Good evening, good afternoon, everyone. Welcome to our parallel session, Response of Terrestrial Ecosystems in the Context of Global Climate Change in the GEO Virtual Symposium 2021. Today we have three speakers in this session. Firstly, I'd like to briefly introduce this session. In this session, we are going to have two main topics. Firstly, we are going to talk about the response of terrestrial ecosystems in the context of climate change. And the second topic is about the sharing and application of long-term ecological monitoring data. Because of this session have just 1 hour, so we have three speakers first, 30 minutes for these three presentations. So 10 minutes for each speaker. And then we have 30 minutes for discussion. Firstly, there are some advice for our participants. If you attend this session, please change your name as your authorities plus your name. And then if you want to have any comments, you can type into the chat area. If you want to have any questions, please raise hand or request the floor in the chat. I don't know how to use the request the floor, but you can also type into the chat area. So firstly, I'd like to introduce our first speaker, Dr. and Professor Zhu Weimin. Dr. Zhu is the professor from International Institute for Earth System Sciences, Nanjing University, China. The research of Dr. Zhu mainly focused on the retrieval of vegetation parameters from remote sensing and optimized the calculation of terrestrial carbon fluxes using various approaches, including remote sensing, ecological modeling, and atmospheric inversion. In this presentation, he will talk about the contributions of different drivers to global terrestrial carbon fluxes during 1982 to 2016. Now, welcome, Professor Zhu.
Okay, good evening, everybody. It's my pleasure to attend this workshop. Can you see me and hear me?
Yes.
My topic.
Yes, very good.
Yeah, the title of my presentation is a contribution of different drivers to global terrestrial carbon fluxes during 1982 to 2016. My presentation includes 4 sections. First is the background. As you know, global terrestrial carbon sink has been increasing in recent decades with large interannual variability. What are drivers for these changes and the variability of global terrestrial carbon sink? It's not very clear. So we use a remote sensing driven ecological model named BEPS to simulate the spatial and temporal variations of global carbon sinks and to identify the contribution of different drivers to these changes and in the annual variability. Before we do the simulation, we use measurements at different scales to optimize model parameters. To validate the model outputs, we use models data and to drive a 4-scale geometrical optical model to invert lever index to estimate climate index. We also confuse models data and aperture data to generate long-term series of lever index data, and then we do a series simulations. The BEPS model split the whole canopy into solid and shaded leaves. We consider the difference in the absorption of PAR by these two types of leaves. The solid leaves can use direct and diffuse photosynthetic active PAR, but the shaded leaves can only use diffused photosynthesis active radiation. The total of canopy GBP is a summation of photosynthesis rate of solid leaves and photosynthesis rate of shaded leaves. We use an impact model to separate the whole canopy leaves into solid and shaded leaves. These figures show you the temporal variations of global leaf index during the period from 1981 to 2016. We find in 74 points of global vegetative areas, leaf index increased. In 42.7% of global vegetated areas, leaf rains significantly increased, especially in Eastern China, Europe, and India, but the leaf index slightly decreased in the tropical regions such as Amazon region, Central Africa, and Southeast Asia. We run the model 6 times using different setting of drivers in order to identify the contributions of different drivers to the global terrestrial carbon sinks. First, we validate our global results of carbon sink with using the residual carbon sink published by the Global Carbon Budget. We find overall our model can capture the variations of global residual carbon sink with a determined coefficient equal to 0.56. We also compare the CO2 fertilization of our simulated GBP. You can see on the right side is a photosynthesis CO2 fertilization factor simulated by our model in comparison with the process-based model and the representation-based model, and the experimental results. Our model simulated the CO2 fertilization in between the process-based model and the representation driven models. We also compare our simulated CO2 fertilization factor with the remote sensing data identified the CO2 fertilization effect. This is our results. This is results from the process-based model in the training project. Our model simulated medium CO2 fertilization effect in comparison with the
Professor Ju, we can't hear you.
Professor Ju, no voice now. Professor Ju. Professor Ju, can you hear me?
I'm calling him now.
Can you hear me now?
Yes, now it's okay.
Now it's okay?
Yes, now it's okay.
Yeah, okay.
Yes, from this slide. Professor Ji, are you talking?
I'm calling. Maybe his network is stucking.
Okay.
哦，是啊，我现在还能听到我的声音吗？
现在可以。
啊，现在可以了是吧？
Yeah.
啊，OK， 啊。This is a special distribution of the average NEP during the period from 1981 to year 2016 in the Amazon region and Central Africa and Southeast Asia and East China and the Eurasia forest area, the NEP is larger, above 80 gram square meter per year. This is accumulated NEP enhancement by different factors. You can see the CO2 is
We can't hear you now. Professor Zhu, we can't hear you now.
Professor G is rebooting his computer.
Repairing his computer.
Rebooting his computer. Rebooting. Restarting.
Okay. Yeah, and I think considering about the time, maybe it's time for us to moving on to the next speaker. Our second, after second speaker, maybe Professor Zhu can come back to continue his talk. So Xiaoli, are you ready?
Yeah.
Okay. Our next second speaker is Dr. Xiaoli Ren. She is the Associate Professor in the Institute of Geographic Sciences and Nature Resources Research, Chinese Academy of Sciences. And she also works in the National Ecological Science Data Center. Her research interest is in the carbon cycle model data fusion and ecological informatics. Her presentation today is about the long-term ecosystem monitoring and assessment. Please welcome.
Hello, everyone. Can you see the scene?
Yes.
Okay. My name is Ren Xiaoli. My presentation is about long-term ecosystem monitoring and assessment. This is the work of our team in National Ecology Science Data Center. The moderator of this session, Professor He, is the director of this center. First, I will introduce the long-term ecosystem monitoring, including the overview of our center. The main sources of ecological data include long-term networked field observation data, scientific experimental data, and remote sensing data, and so on. In general, ecology has entered the big data area, and open data sharing of ecological data has become an important driving force to promote the development and innovation of ecological science. The ecological monitoring data have showed the following trends. First is establishing scientific data centers to deploying related projects and developing ecological informatics. Second is to performing network researches based on long-term ecological monitoring data. Third is sharing data through data and data paper publishing. In 2019, the Ministry of Science and Technology established 20 national science data centers in China. And our data is one of the ecological data. Our center is based on the existing national stations and with the data of ecosystem observation and research as a core, expand the departmental stations and the thematic observation networks, integrate the station, region, and the national ecosystem observation and research data products. Long-term monitoring data of field ecological size is the core and the most distinctive data size of the center. Based on Chinese Ecological Research Network, we have systematic, standardized, and high-quality in situ observation data for almost 2 decades, including biology, soil, hydrology, atmosphere, and different ecosystem types, such as forest, grassland, cropland, and so on. CERN have 44 stations around the whole country for now. The major missions of the network is monitoring, research, and demonstration. Monitoring is to obtain scientific data of ecological change by using different approaches, such as long-term dynamic monitoring, ecological experiments. Research is to study the changes in structure, functions, and processes of different ecosystems. Demonstration is to provide technical and scientific suggestions to decision makers for national ecosystem management. And CERN has established the standard indicators, standard methods, and standard instruments to conduct measurements and to standardize the network-based observation and experiments. CERN has now formed routine long-term ecosystem monitoring for almost 20 years. The data measurement and quality control all follow the standardized technical specification to make sure the quality of the data from the stations to our center. The data has been open shared through various approaches, such as information systems, data books, data journals, and international platforms. We constructed a member node in DataONE to share data to international users in 2018. This year, the National Ecosystem Data Bank is online. This one. We have shared long-term forest ecosystem monitoring data on this platform, and welcome to share your data on this platform. The second part is ecosystem assessment. Based on the long-term co-located monitoring data and other sources of data, we have performed site scale and regional scale ecosystem assessment. On site scale, we want to provide data benchmark and to provide carbon cycle research baseline using this size with few disturbance and to help model evaluation and development. The field data is discrete, so we use model data fusion method to construct the continuous time series data, and use this data. We have constructed some research results, such as we use time series data of 10 forest plots in eastern China, and we found the steady state assumption of ecosystem models underestimated the carbon turnover time by 30%, so leading to a four-fold underestimation of night ecosystem production in the large carbon uptake region is the East Asian area. On regional scale, we assessed the effect of climate change and human activity on ecosystem carbon cycle for regional ecosystem function and service assessment. The data source is 74 size-year flux data from 11 sites of China flags, and the carbon stock data of over 11,000 plots from field survey, and use three process models to simulate the night ecosystem production of China in the last 30 years. And we found the monsoonal regions is the eastern part of China, dominated the carbon sink of China, contributed to over 80%. And we found the carbon sink showed an altered trend from about 2000. This decadal scale shift from a downtrend in the first 2 decades to the last 1 decade. The simulation experiments revealed that climate change were the primary factor that led to this altered trend. And the stress and summer monsoon stimulated carbon uptake, and the warming hiatus lessened the decrease in this trend. The conclusions are incorporated into the fourth National Climate Assessment Report of China. This is the products we constructed. You know, the data on the site is not continuous, so we constructed the continuous data for almost this is 10 the size, and this is the regional carbon sink of China for the last 30 years. The third part is international cooperation.
You have 1 minute left, okay?
Okay. International cooperation. We have cooperation with GEO in 2019, and have completed the implementation plan for GEO community activities. We also cooperate with DataONE to share our data on the DataONE platform. This is a cooperation with other long-term ecosystem monitoring and assessment instruments. This is our team. Okay, my presentation is over, please. Thank you.
Yeah, thank you, Xiaoli. It's just in time. So, Professor Zhu, are you ready to move back to your presentation?
Yes, I'm ready.
Okay, please go on.
Yeah, can you hear me now?
Yes.
Yes, I'm sorry for the problem of my network. Now my presentation includes 4 sections. First is the background. As global carbon sink has been increasing in recent decades with larger yeah.
I think you can continue with the presentation. I think the next few slides. Yeah, next.
Okay. Okay, from here.
Yes.
Okay. Yeah. Okay. Yeah, from here now. This is the average NEP during the year 1981 to year 2016 simulated by our model. The largest carbon sink is in the Amazon region, Central Africa, and Southeast Asia, and East China, and Europe, Eurasia forest area, and East United States. This is a contribution of to the accumulated NEP during the last 40 years. The largest contribute to the global carbon sink is the CO2 fertilization, followed by leaf index, and then nitrogen deposition. Climate has a negative effect on the global carbon sink. What's the reason for the negative effect of climate change? You can see that climate change has a negative effect on global GDP. It induced the decrease of almost 78 PG carbon of GDP. Although the climate change has also induced the decrease in the ecosystem respiration, but the decrease of ecosystem respiration is smaller than the decrease of GDP. So climate has a very large negative effect on the global NEP. As though different regions, climate change has a negative effect on NEP in all regions. The CO2 has a positive effect on NEP in all regions. For China, the leaf index has a secondary contribution to the terrestrial carbon sink due to the afforestation in recent years. This is a figure shows the contribution of land change to the leaf index change and NDVI change. You can see the increase of forest and the decrease of short vegetation enhance carbon sink in vice versa. It means the increase of forest and decrease of forestation induce large increase of leaf index and consequently NEP. CO2 fertilization has a positive effect on carbon sink in all regions, especially in the tropical regions. Leaf index has a positive effect on NEP in Eurasia region and East China. This is the dominant factors affecting the global carbon sink. Climate was a dominant factor inducing the decrease of carbon sink in 18% areas. Leaf index changes acted as a dominant driver for the increase and the decrease of carbon sink in 44 and 0.6% of areas. CO2 and nitrogen deposition changes was a dominant factor drivers for the increase of carbon sink in 36% and 0.2% of areas. This is my conclusions. In 83 global vegetation areas, leaf index significantly increased. Accumulated global carbon sink during the year 1981 to year 2016 was 95 pg carbon, CO2 leaf index change, nitrogen deposition change, and climate change is contributed 45, 12.1, negative 27 pg carbon respectively. Climate change was a dominant factor induced decrease of carbon sink in 18% of areas. Leaf index and the CO2 change acted as a dominant drivers for the increase of carbon in 44% and 36% of global vegetated areas. That's all. Thank you.
Thanks, Professor Zhu. Now it's time for the third presentation. It's from me. My name is Xinyu Zhang. Can you see the slide?
Yes.
Yes.
Yeah. I come from the same institute of Xiaoli Ren, and this is a brief introduction about our ongoing research program. It's a key program for international science and technology cooperation projects of China. It's just started in the end of 2020. So mostly I will talk about what we will do in the next 3 years. The title is about comprehensive observations and applications for typical terrestrial ecosystems in China and the Central Asia region. I will talk first about the background. In 2015 to 2030, the United Nations Sustainable Development Goals has set the goals of ensuring conservation, resolution, and sustainable use of terrestrial ecosystem, and also to combat the desertification. And for 2030 regional strategy for sustainable development in Central Asia, they think solving the ecological and environmental problems in Central Asia determines its social and economic development. However, in Central Asia, ecosystems are fragile, ecological problems are becoming more and more serious, and the ecosystem services are degrading. So it's urgent to build an international coordination mechanism in the region to unify ground monitoring protocols and ground, near ground and satellite integrated monitoring and evaluation technologies to support the protection, restoration, and sustainable use of ecosystems and their services. But however, in this moment, there are still many problems. There are three key problems in this area. The first problem is in this area, it's lack of high quality ground monitoring data in Central Asia, and it's necessary to build a terrestrial ecosystem ground monitoring index system, technical protocols, and information system in Central Asia. For the second problem is lack of an integrated ecological monitoring and evaluation system. For ground monitoring and satellite remote sensing, they all have some advantages, but all have some disadvantages. So combination is not tight and difficult to support the evaluation. For this project, we want to make some ecological monitoring and evaluation system fused with the remote sensing, unmanned aerial vehicle ground to support the comprehensive monitoring and evaluation of the Central Asia ecosystems. For the third problem is that in this area is lack of international data sharing mechanism and no GEO Knowledge Hub in this area. So we set the general objectives of this project is to support ecosystem service assessment and monitoring technology for Central Asia. We set 4 tasks in this project. Firstly, to integrate ground monitoring technology of terrestrial ecosystem. Second, to establish monitoring data management and analysis system. Third is to develop ground, near ground, and satellite remote sensing comprehensive monitoring and evaluation technology. Finally, to establish an international coordination mechanism for integrated monitoring and application of typical terrestrial ecosystem. The second part is about the method. In this project, we selected 27 terrestrial ecological stations in the China and Central Asia region. And we also selected degraded grassland in Tajikistan as demonstration area. This slide shows the technical scheme of this project. Focus on the supporting ecosystem service evaluation. Based on the China and Central Asia ecological networks, we are going to formulate technical protocols for ground monitoring and the development of monitoring data management application system. Based on the comprehensive monitoring of ground, near ground satellite technologies, we are going to develop a comprehensive monitoring and evaluation system to establishment of grassland vegetation status assessment technology. And we are going to establishment of a regional ecosystem monitoring alliance, build an international coordination mechanism to make some technical training and academic change in this region. For task 1, we want to construct protocols for monitoring and data product. The main technology we are going to use are expert knowledge, screening and optimizing, and method comparison to make the technical protocols for monitoring and the protocols for monitoring data quality control. For data, we are going to use the data integration, statistical analysis, and spatial analysis to make the protocols for monitoring data product development and to make key data products. For task 2, we are going to use some WebGIS and mobile app and workflow technologies to make data management and analysis platform, including data aggregation subsystem, quality control module, and data product processing subsystem. This work will make some basic support for the demonstration. For task 3, we are going to construct and demonstrate of comprehensive monitoring and evaluation technical system of grassland ecosystem in Central Asia. We are going to combine the ground and the near ground fusion technology and the near ground and the remote sensing fusion technology to evaluate the vegetation coverage and the stocking capacity and the biomass in this area. Hope we can have some comprehensive monitoring and evaluation of typical grassland and the national grassland in Tajikistan. For this task, we are going to select the demonstration area for comprehensive monitoring and evaluation of grassland ecosystem in Tajikistan. We select 3 typical degraded grasslands to carry out ground monitoring and unmanned aerial vehicle observation. We are also going to select 2 belt transect. With these 2 survey belts, we are going to set 3 to 4 observation points for each belt for UAV observation. We are going also to carry out application demonstration of national grassland ecosystem monitoring and evaluation in the Tajikistan nationwide. For task 2, we are going to establish the China and Central Asia Regional Ecosystem Monitoring Alliance and develop the portal of the China and Central Asia Regional Ecosystem Monitoring Alliance to build a GEO Knowledge Hub for typical terrestrial ecosystems in the Central Asia region. For the last part is about the progress. During the last 2 decades, China's ecosystem research network have compiled 3 sets of long-term observation and quality control technical protocols, and also accumulate systematic and standardized data from 66 field stations of different ecosystem types in China and also in Central Asia. We also developed an ecological information platform. The Station Center collaborated cloud platform for Chinese Ecosystem Research Network and also for Chinese National Ecosystem Research Network have covered the cycle of ecosystem data collection, aggregation, storage, analysis, and visualization and sharing. The Chinese Academy of Sciences have built ecological environment and resources service platform for Central Asia to boost information sharing in this area. The research group also researched some methods between the remote sensing and the ground sensing. We use the UAV LiDAR to extract vegetation parameters of Inner Mongolia grassland and found the UAV LiDAR sensor significantly underestimated the grassland canopy height, which must be calibrated before use for biomass estimation. We also built a flowchart for developing the fused growing season NDVI map based on the RPRFM. It's difficult for a single sensor to obtain remote sensing data with high spatial and temporal resolution simultaneously under existing technical conditions. Hope these spatial temporal fusion methods will provide an effective way to generate both high temporal and high spatial resolution data for monitoring dynamic changes of land surface and biomass in the Tajikistan area. And based on our research center for ecology and environment of Central Asia, we are negotiating to build an alliance of China and Central Asia for ecosystem research monitoring. Now we are also investigating the protocols and standardized methods from the main advanced research network around the world. This is the protocols we are investigating in the American National Ecological Observatory Network. This is the protocols we investigated in the Environmental Change Network in the United Kingdom. And we also collected some documents relative to the ecological monitoring in Central Asia. And we have also investigated the stations, including their sites, variables, protocols, products, etc., and information infrastructures. Now we have collected 10 stations meteorological data from Central Asia. Now we also developed a new version of integrated station management information system, developed and trial operating on several stations, such as in Hulunbuir in the grassland ecosystem. Now we also evaluate the spatial-temporal variation of grasslands from 2000 to 2020 in Tajikistan. And using the MODIS NDVI data, we have found that GSN of Western grassland is higher than the eastern part, and the GSN of grassland is increasing in the last 20 years, indicating an evident recovery of grassland in this area. That's all from me, and thank you for your attention. Now we have finished all the 3 presentations. Let's move on to the discussion part. Now, if you have any comments or questions, please raise your hand or type into the chat area. Professor Zhu, I have a question for you.
Okay.
At the last slide for your conclusion, you said the climate dominates the changes. So I'm wondering, have you considered about the human activities in that research?
Oh, okay. This is a good question. The human activities is not explicitly considered in our research, but is implicitly considered through the effect of human activities on land use change and on different texts. Yeah, for example, the human activities can make the conversion of forest to short vegetation like crop and grassland, and also can convert the grassland to forest. This conversion will induce the change of different texts and also induce the change in the turnover rate of different carbon pores.
Mm-hmm. Okay, thank you. Are there any other questions? There is a question in the chat area for all the panelists. Is your work connected to supporting policymakers directly in some way? Are you participating in the UNFCCC process to some extent? So that's a question from the GEO. So, Professor Zhu, would you like to talk about this question first?
Yeah, I think for my research, we just provide some scientific data to the policymakers. For example, now in China, where the central government is making great efforts to balance the carbon emission through the anthropogenic activities and the carbon sequestration by terrestrial ecosystems. So the central government is urgent to want to know how much of the carbon can be absorbed by the natural ecosystems like forests and grassland and crops. So I'm a modeler, so I can provide the scientific data for the central government to help the clever decision of the policies.
Yeah, yeah. Especially at this moment, many people want to know the results.
Yeah.
Yeah. And for my application research projects, we hope in the next 3 years, we can supply some data for the Central Asia area to evaluate the grassland biomass or their carbon storage. Hope it can make some support for the government's consolidation. Yeah, that's from my point. Yeah. And Xiaoli. Yeah, would you like to talk about this according to your presentation? I can't hear, Xiaoli. I can't hear you. Yeah. Can you speak again? You can try to speak again. Now we can't hear Xiaoli at the moment. Are there any other person who have involved in the GEO work or want to talk about the climate coordinator at the GEO?
I think the terrestrial ecosystems in East Central Asia and can you hear me, Professor Zhang?
Yes, yes, we can hear you, Professor Zhu.
Yeah, I think your data and your work is very, very important because terrestrial ecosystems in Central Asia and Northwest China.
Mm-hmm. Yeah. As a modeler, you think what's the most important data to support the carbon dioxide assimilation in that area? Yeah, Sarah said the how you use is used by national government. Exact question, because the GEO Secretariat can support sharing your research internationally with policymakers and UNFCCC focal points from different regions. That's great. Hope we can show some interesting results in the next meeting or in the near future. Thank you. So Lee, can you make your comments or explanations now? We still can't hear you. So according to the timeline, we need to finish our parallel sessions in 9:30. So Xiaoli, now we can see you. Do you want to make any comments now?
Can you hear me?
Yes, now it's okay.
Oh, finally. Yeah. The long-term in situ observation data can be used to assess the ecosystem status and the variation trends in China. And the data have been used in the national assessment. And about the climate change, the meteorological observation data in the field size is different with the stations in the urban areas. I think this is some contribution to the climate change research. Yeah.
Okay, thank you. According to the timeline, I think it's time for us to sum up our sessions today. Today, we have 3 presenters to talk about their publications of their work or the projects we want to do. So for in the near future, we want to contribute our work, especially like carbon for assimilation for global climate change, and also especially in China and Central Asia area. And hope we can show our further results in the near future. Thank you all for your attending and attention. That's all from this session. Thank you. Bye-bye.
Bye-bye.
Bye.
Bye.
小丽，是还需要上传一个就是会后的那个 highlights 吗？
哦，邮件里好像是那么写的。
你看一看吧，需要上传一个什么的话，是不是一张 PPT 啊？什么就是我们的3个报告是吧？
对。
OK。
对。
Hello, Alan. Do you have any questions or comments? We can't hear you.
Still no voice.
Hello?
Hello.
Yeah.
Can you hear me now?
Yes. Clear?
Yeah, thank you so much. I say that the presentation was quite well. It was quite eye-opening. I'm working on some wetland restoration. So I got to get some ideas from here because I'm trying to use GIS and remote sensing in monitoring them. So I really enjoyed this the presentations that we got.
Thank you.
Yeah.
Okay.
Thank you. Bye.
Bye-bye. Bye.
I'll get in touch through email.
Yeah, sure.
Yeah, thank you so much.
Yeah, thank you. Bye.